Good morning, fellow nerds, and welcome to another episode of Between Two Nerds. I'm Jeff Doyle, and with me is my friend and co-host, the excitingly handsome Jeff Tansura. Good morning, Jeff.
Good morning, Jeff. Great to see you. Great to see everybody else. Thanks for joining us today. How are you doing, Jeff?
We've got a very special guest today, and Jeff, you want to do the intros?
Yes, absolutely. We would like to welcome Dr. Tony Lee, old friend.
I'm not that
old colleague. And so the reason we meet today is routing in data centers, as always. And if we go back a bit, a couple of years ago, we decided, we being ITF, that we really need to work on set of new protocols or extension to existing protocols to make routing DC better, more stable, scaling better. And it resulted in some new work. So we've been talking about Rift for the last 4 episodes, which was one of the outcomes. There's another new protocol called SVR, which is really BGP, where best path is replaced by SPF. So those are 2 new protocols.
Mm-hmm.
Tony decided to work on existing routing protocols and make them better. And this is the topic of today's discussions. What has changed in a way we use, or we could use IGPs in densely matched topologies? And Tony has been leading this effort. And I'll go to Tony. He will present his slides and tell us about what's going on, what has been done in ITF and the industry, what has been implemented.
So
Thank you, Jeff
Tony.
and Jeff.
We're really excited to have you.
Great to be here. Thank you. All right. Can you guys see slides?
Yep, coming up.
We do.
All right. So what I'm going to talk about today is called dynamic flooding. And we have 3 internet drafts that have already been published. The first is all of the protocol changes that we talked about. And then the second one is the algorithm that Arista is proposing. There are multiple algorithms that we can use, and we're disclosing what our algorithm is. And then we also have a draft that is a Yang model for enabling this feature. So the basic problem that we're trying to deal with is, how do you deal with flooding on a leaf spine or a CLO network or some other kind of dense topology? With a really dense topology like this, the flooding that is normally in a link state protocol is extremely redundant, and it's very synchronized. Let's suppose we've got a leaf spine network with, say, 10 spines and 1,000 leaves. Well, okay, we've got thousands and thousands of links, 10,000 of them, in fact, and we're going to get 10,000 copies of every link state packet we flood around. That's not very helpful, and we actually really only need a couple of copies. So what we found out a long time ago when we started building these data center networks is that we ended up with flooding storms. They're really annoying because any single link change causes link state protocol packets to be generated from both ends of the link. And those protocol packets are flooded. They go up to a spine, they go back down to all of the leaves, and all of the leaves in synchrony broadcast them right back up all to the other spines. So in our 10-1000 topology, we get 1,000 copies of every link state change all at the same time. Leaf spine networks are basically giant packet amplifiers, and we're doing this to ourselves, and we're basically causing a DOS attack against our own network. If that becomes bad enough, we start dropping packets. And once we start dropping packets, we start dropping the hello packets. And then it looks like we've had another link failure. And pretty soon this just cascades, we start generating more link state packet updates, and pretty soon the entire network just falls apart. Okay, well, this is really, really quite silly because we don't need this much flooding. We don't need to use the entire topology. If we flooded over a subset of the topology, then we could still have very robust communication. We could see all of the topology changes, and we wouldn't need all of this packet amplification. So here's a basic idea. What should that topology be? We call that the flooding topology, and everything we're going to talk about is how to compute the flooding topology. Now, there are lots of different goals we have in mind. We want to address various dense topologies. We don't want to deal with just leaf spine. Many people are building other kinds of interesting topologies, super spines, planar networks. Some people are still doing hypercubes and other strange things. We want to be general. And so one of the things we're going to do is to very much focus on covering all of the things we know about and also cover complete graphs. A complete graph is one where every node is connected to every other node. And it's a superset of every other network that you can think of. So if we can deal with that, that's the densest possible network, then we can probably pretty much deal with anything at all. Let's see, what other things? Well, in our flooding topology, we want no single point of failure. And we usually have only single points of failure at any given time. So that's the dominant mechanism for failures. And so we want to make sure that the loss of any link or node will not hurt convergence too badly. Note that we're not trying to deal with many multiple failures. If you lose half your data center, well, not much we can do to fix that. That's just, power failure and everything's going to break loose. We very much want to limit flooding propagation delays. You can imagine a flooding algorithm that created a topology that caused link state packets to go hop by hop all throughout the network with no copies and basically giant ring, and it would take forever to get around. So we actually want to keep the flooding topology kind of tight. And in graph theory, theoretic terms, what we say is we want to minimize the diameter of the flooding topology. We don't want to centralize the flooding. We want to distribute the work. Okay? So let's go back and look at our leaf spine network. If we've got 10 spines and 1,000 leaves, well, we don't want all of them flooding to just one of the spines. That gives us a scalability limitation, if nothing else. It also makes us very, very likely to have a problem if we lose that particular spine. So how about we work to distribute all of that? The flooding should be done equally across all of the nodes as evenly as we can. And finally, well, we expect that when people are going to do this, we have other things in our IGP. So the area where we're doing this flooding is probably part of another larger IGP area. So we want to be careful and make sure that we're not doing things that are too strange that don't interact well with the rest of the IGP. So these are the goals that we're trying to accomplish. Now we came up with a couple of different ways of doing this. And we thought that doing this in a distributed fashion is kind of challenging. We've actually done SPF in a distributed fashion, but that's the most complicated algorithm that we've ever made work, and even getting that working has been quite challenging at times. So in doing this, we recognized that having the flooding topology algorithm that was distributed might be very, very challenging. And so to avoid doing that, we propose doing things in a more centralized way. There is an option for doing distributed. I'm not going to talk too much about that. Centralized approach, the way we start is by picking an area leader. and just picking one node in the area, and he's going to be the one that does the computation of the flooding. The mechanism here is very similar to designated router election, except instead of just looking at what's on the link, it looks at the whole link state database for the area. Nodes that are willing to be area leader advertise that fact. They advertise a priority. We simply pick the highest priority, and then as a tiebreaker, the highest system ID. Once we have an area leader, the entire area will recognize that and listen to the flooding topology that the area leader is going to advertise. Encoding this into and distributing it as part of the link state database is pretty straightforward. We chose a mechanism for encoding that we could make it as terse as possible. That makes it a little messy, but pretty much what we're doing is describing paths within the network, and the union of those paths becomes the flooding topology. Normal link state mechanisms, link state flooding mechanisms are all still working on all the links. So no major changes here. We're just restricting which links we're flooding on. When the area leader does see a topology change through normal link state updates, he can also update the flooding topology. Now, there's no need to update if the topology change doesn't involve a flooding topology. If you lose a link that was not on the flooding topology, that's not a big deal. But if there was a failure in the flooding topology, then the area leader may want to make some changes. If we have a change that is going to change the flooding topology in such a way that the area leader can't see it right away, for example, if there's a new node that's coming into the topology and it will not be on the flooding topology yet, then that node can request temporary flooding from its neighbors until the area leader sees it. So this helps eliminate some corner cases. Now you can do things in a distributed fashion. Again, if you do this, very hard to debug, going to be much harder to standardize and achieve interoperability. We did manage this for SPF, but we've never managed this for anything more complicated. We invite people to go ahead and try, but I'm not personally optimistic about getting that into production. We spent a lot of time simulating how dynamic flooding behaves, and this is just a little bit of theoretical work on how it would grow with large networks. This is a surface, so it's a three-dimensional graph. The number of leaves is on the x-axis. The number of spines is on the y-axis, so more spines going back. And the amount of improvement that you get, i.e. what percentage of links are you not flooding on, that's on the z-axis. And as you can see, as you go to large numbers of spines, 32 spines say, and thousands of leaves, you can see very quickly you eliminate almost all of the links. Up to 95% of the links just go away very quickly. So we have a lot of hope that this is very, very productive. And we sat down and started playing around with some graphs. So we started off with a complete graph. This is K10, complete graph on 10 nodes. And you can see the dashed lines are data links, and the solid lines represent the flooding topology. And different colors indicate different iterations of our algorithm picking the flooding topology links. So it's an iterative algorithm that works until it's covered the entire graph. So as you can see, you're flooding only on 2 or 3 links per node, and the rest of the links, data links, are there, but we're not doing any of the flooding on it. Everything is connected twice, bi-connected. So we've got actually very good solid connectivity. And the diameter of it is relatively restricted. There's basically 2 or 3 hops to get anywhere. Here's a more typical example. This is a leaf spine network. Let's see, we've got 17 leaves and 4 spines. And again, dashed lines are data only, and the solid lines are the flooding links. And you can see only 2 of the leaf links for each leaf. So we have full by connectivity. And most importantly, we've distributed the work. The number of solid links on each of the spines is well distributed. And to expand things, if we take a look here at a super topology, we have super spines above, a layer of spines, and then lots and lots of leaves at the bottom. And with topology, that's actually pretty well distributed. Okay. Pure data links are not shown in this graph because otherwise the page would be black. And here's a closer look at another leaf spine. This one, 4 spines and 60 leaves. And again, you can see we've done a nice job at distributing all across all the spines. And the leaves are only black. So we implemented this, and we sat down and actually booted it up. We simulated a leaf spine network with 4 spines and 60 leaves. We sat down and used TCP-Dump to look at the packet traffic. Now, because of TCP-Dump, we were being pretty liberal. We ended up counting both the LSPs and the hello bits. And in the original native ISIS, when we do this, we stabilized and came up with 110,000 packets as seen by the spines and 15,000 packets seen by each of the leaves. If we enable dynamic flooding, the same thing, and we need 41,000 packets at the spines and only 3 packets down at the leaves, reducing things by 62 and 77%. And this is just with 4 spines. So where we are, we've got a base spec that's in the LSR worker. That's just churning along. We're progressing to the standard, no outstanding issues. We're really waiting for deployment report. So far, we don't have anybody who's willing to stand up and say things in public. We have a Yang model in the draft. Arista has documented our centralized algorithm. It's out there with PR barriers. It's in you won't sue us, we won't sue you restriction. So you're free to put that out there. We implemented the ISIS, and that's already tested and shipping. And our feature documentation for this is already on our website. So that's all I had. Any?
I'll ask you questions. So the base spec covers both SS and OSPF, and this is what we do these days in link state routing working group. We cover both protocols. Is there any difference in results achieved in OSPF as compared to SS?
Theoretically, no, it should be exactly the same. We haven't done the implementation yet.
This is, I mean, looking at this whole concept, obviously, for link state protocols, you know, pretty much the history of link state protocols is how do you control flooding? I mean, you know, it goes all the way back to areas and mesh groups and pacing timers and, you know, what, partial SPF and all those kinds of things. And this looks really promising in terms of making link state protocols protocols in general a lot more scalable. Do you see this being applied outside of the data center? I think you kind of alluded to it in one slide, but do you see this as something that has a wider application?
Certainly applicable in any dense topology. Sparse topology, the algorithm runs fine, but it can't do much in terms of reducing the actual flooding topology. So it's not very useful.
Yeah.
It can basically be done anywhere without too much of a problem. Can it be used outside the data center? Yes, absolutely. Not a problem at all.
It's exciting.
Looking at all the enhancements, if you look into your past and you still remember times where networks with 2000 ICS node would melt down. If you would apply what you do today to network you observed 20 years ago in large ICS backbones, do you think it would have been better?
Yes, absolutely. One of the first networks where we saw cascade failures was a fully connected, complete graph of nodes on an ATM network. That was only 20 nodes at the time. And that caused exactly this problem. And at the time, we came up with ISIS mesh groups to reduce the flooding topology. That was manual configuration and allowed you to manually configure what you wanted your flooding topology to be on a static and link-by-link basis. Obviously, that's not very maintainable. And so one way of looking at this is that dynamic flooding is basically an automation of mesh groups.
I think all of us remember configuring mesh groups on frame relay and ATM networks and how much hassle it was. And it was completely manual job indeed. In terms of enhancement, what do you think still needs to be done? Where do you see further enhancement to your work?
So I think we're in a pretty good spot right now. Obviously, we'd like to see other implementations. Some other people have done some things, but I don't want to comment about other vendors' implementations.
So far, you haven't tried to interoperate with anyone else. I've seen announcement of Cisco implementation. I didn't look into details.
Yeah, the problem we have here is that if you have a distributed implementation, you can't interoperate with a centralized implementation. And even if you've got a distributed implementation, you can only interop with other people using the same algorithm. We do support multiple algorithms, but that means multiple implementations have to select the same algorithm. And nobody's willing to implement somebody else's algorithm so far.
But we are looking forward to some negotiation of algorithms in the way we've done for flex algos and other stuff. So at least you can signal what support is and do kind of capability negotiation similar to BGP to agree on something, right?
We have the mechanism for negotiating that. That's true, but nobody's actually been willing to write the code. And without that, the distributed version doesn't work. And no one else has been willing to put forward a centralized implementation yet. So we don't have interoperability.
Okay. So probably a question of time, and hopefully eventually we'll agree on something that works for everybody. And obviously it's up to us customers of yours to beat you up, to implement something that works on every vendor and for everybody.
Absolutely. Start beating vendors, please.
Guys, please be vocal about what you prefer, what you would like to see, and eventually we'll make them work. And
yeah, just looking at sorry, Jeff, go ahead.
Jeff, go ahead.
Oh, I was just going to say, related to that, just looking at the internet draft itself. I've got that up on a different screen here. I mean, Tony, you're the editor of this, but under below Arista Networks, there's there's people from Cisco, there's people from FutureWay, Juniper Network, CenturyLink, Verizon, AT&T. So some users that certainly could be pushing, but also quite a few vendors there. Do you see that as an optimistic thing, or is that just sort of a IETF thing?
People are
optimistic in terms of vendors developing this.
Yes, I think that's a good thing. People are certainly willing to collaborate. They're certainly interested. But now we're to the point of actually the rubber hitting the road. And so now people actually have to implement and then actually deploy.
Yeah, so it's not a big secret that most of large tier ones are trying to re-architect their network in a more distributed way and replace large chassis by really leaf-spine topologies. We've seen presentations from Comcast on Nano. We've seen presentations from, I would say pretty much every large tier one in US in one another public forum. They all talk about distribution and more distributed networking. And most of them actually run ISS due to better scale. I mean, this is traditional IGP in service providers world, right? So I would think that outside of data center, we'll see implementation of such technologies in this kind of distributed fabric that replace large multi-chassis core routers.
That is the hope. It's called the deaggregated core router. And yes, we are hoping to see lots of people go this direction. If they do, then this is maybe very applicable.
Additional question. So there's quite some work on optimization of flooding with regards to number of retransmissions, how to provide flow control. How do you see the two pretty much different? They're trying to optimize towards different goals, but eventually they'll come in the same routing protocol. How do you see these two working together?
So fortunately, they're actually very much orthogonal. The flooding speed is just trying to do some more sophisticated things in the flooding mechanisms themselves. Because the original flooding specifications were designed for people with very, very primitive processors and not a lot of memory. And the pacing is rather slow for current convergence needs. So what we're trying to do is to understand exactly what we can do to change those flooding algorithms. People have been operating outside of the boundaries of the strict specification for quite some time, and we don't have any uniform ways of putting things forward and interacting between systems. What I'd like to see is a better feedback mechanism so that we have a control loop between the transmitter and the LSP receiver so that we can actually cause flooding to saturate the link and saturate the receiver's processor, but not exceed that.
So you don't, I mean, in many implementations, buffering is implemented per interface rather than per neighbor. So in this case, amount of flooders is significant as well, not only amount of data you flood. So wouldn't it make things a bit better?
So yes, you have some interesting complications because our architecture is different, and understanding what the rate is that each can accept is actually non-trivial. But what we're trying to do is to create a real control loop so that a receiver can tell the transmitter exactly how fast the transmitter is going.
Great. And actually, I think this is really fascinating work. It's really hot discussion, and I'll start working group, and eventually we'll bring it up into discussion here. So potentially one of upcoming podcasts. Jeff, do you have any more questions for Tony?
I do not. I'm fascinated by this also, and very interested in learning more. And Tony, thank you so much for taking time out of your day to educate all of us on this what I consider a really important and really interesting trend.
Well, thank you, Jeff. This has been fun.
Thank you so much, Tony. And please provide your questions so we will let Tony know if there are any additional questions. So there's a lot of work in IETF going on. You could review recordings LSR on Tony's presentation over the last couple of years. There have been a couple of presentations, none on exactly this topic, and we'll continue covering it. There's some progress, and I would really like personally to see some alignment between vendors to support at least one single common algorithm to be able to build network, just being multi-vendor. Thank you so much, Tony.
Thank you. I look forward to
Absolutely.
getting more interoperability too. Thanks very much. Bye-bye.